Thanks. Okay, so we're going to go from Francis Bacon to Michael Faraday, so I'm just going to sort of launch straight into this. I guess it's true to say that for most of the time in Western civilization, mainstream orthodox thinkers have tended to subscribe to the view that physical interaction takes place by contact, and that action at a distance is impossible because a thing cannot act where it is not. Of course, there have always been subscribers to a belief in occult influence, and these thinkers have had a greater inclination to accept that action at a distance is possible. But for most of Western history, since the ancient Greeks, I think it's true to say that this has been a minority, unorthodox view. The major historical period when this was not true was the period marked by the ascendancy and establishment of Newton's authority, when action at a distance became an accepted aspect of physics. Future historians might also look back to our own time and see this as a second period of belief in actions at a distance, or quantum entanglement as it's now called, but we'll just have to wait and see how things develop there. Okay, so the dominant view was summed up and authoritatively established in the 13th century by Thomas Aquinas, when, echoing Aristotle, he wrote, "No agent can operate immediately where it is not." By the way, my slides are just to provide the quotations, and I'm going to read them out anyway for the sake of the sort of recording, but they're there for you to see, and just so you know, I'm not making this up. So this was still the dominant view in 1690, when John Locke wrote in his widely read and influential essay concerning human understanding that it is impossible to conceive that bodies should operate on what it does not touch, which is all one as to imagine it can operate where it is not. Now, as far as we can tell from his writings, Newton subscribed to the same standard assumption about the nature of things until 1679, when he was led by a couple of independent considerations, which I'll come to accept that actions at distance might be possible. His earliest discussion along these lines appears only in an unpublished manuscript, 1679. Air is expanded to double or treble or even 100 or 1,000 times its normal space, which would hardly seem to be possible if the particles of air were in mutual contact. But if by some principle acting as a distance, the particles tend to recede mutually from each other, reason persuades us that, and so he goes on. But by the time he published the Optics in 1704, he was bold enough to state his suspicions perfectly explicitly in print, in the influential queries added to the end of his unfinished study of light. He wrote, for example, I'm using the numbering of the queries from the 1717 edition here. Query 1, do not bodies act upon light at a distance and by their action bend its rays? And is not this action cateris paribus strongest at the least distance? Query 29, pellucid substances act upon rays of light at a distance in refracting, reflecting and inflecting them, and the rays mutually agitate the parts of those substances at a distance for heating them, and this action and reaction at a distance very much resembles an attractive force between bodies. And query 31, the longest and most sort of forceful and influential of the queries, have not the small particles of bodies certain powers, virtues or forces by which they act at a distance, not only upon the rays of light, but also upon one another for producing a great part of the phenomena of nature. Now, these are entirely explicit, but the discussion of gravity in the Principia also seems to depend on actions at a distance, even though he never explicitly uses the phrase action at a distance anywhere in the Principia. He was explicit in suppressed drafts of the preface and a conclusio that he wrote for the Principia, but was more cautious in what he actually sent to the printer. But he didn't have to be explicit, as Alexander Quire has pointed out. The Principia seemed fully to confirm that his teaching could be and was interpreted as positing action at a distance by an attractive force residing in bodies. So I hope I've established that Newton really did turn to actions at a distance as real possibilities in his physics, in which case we're immediately presented with a problem. Why did Newton reject the standard view that bodies cannot act where they are not? What made him make this surprising move towards the acceptance of actions at a distance? In part, the answer resides with technical issues in Newton's physics, and I'll return to those. But first, it's important to note that at precisely the time when Newton was hitting his stride as a natural philosopher, actions at a distance had already begun to make an appearance in English natural philosophy, and could be seen, therefore, as a notion to which Newton might have legitimate recourse. This more positive attitude to actions at a distance can be seen in the highly influential works of Francis Bacon, for example in his Wisdom of the Ancients, which is Bacon's most successful philosophical work during his own lifetime. And if you haven't read it, I recommend you should. It's fabulous stuff. So Bacon writes in the essay called Pan or Nature, "The body of nature is most elegantly and truly represented as covered with hair, an allusion to the rays which all objects emit, for rays are like the hairs or bristles of nature, and there is scarcely anything which is not more or less radiant. This is very plainly seen in the power of vision, and not less so in all kinds of magnetic virtue, and in every effect which takes place at a distance. For whatever produces an effect at a distance may be truly said to emit rays. But Pan's hair is longest in the beard, because the rays of the celestial bodies operate and penetrate from a greater distance than any other." And then later in the essay called Cupid or the Atom, "Now whoever maintains the theory of the atom and the vacuum, even though he supposed the vacuum not to be collected by itself, but intermingled through space," that's intermingled with the atoms of course, necessarily implies the action of the virtue of the atom at a distance. For without this no motion could be originated, by reason of the vacuum interposed, but all things would remain fixed and immovable. So, if there's no action at a distance, then the separation of the atoms by vacuum would mean there could be no transmission of motion without action at a distance. Okay, similarly, in what is now regarded as his most influential philosophical work, the Novum Organum of 1620, Bacon insisted that there are other powers which work at a distance, albeit a very small distance. Few have yet been noted, though there are more than men imagine. For instance, to take examples from common objects, amber or jet attracts straws. Now, I've missed out a few trivial ones there. And the magnetic power which draws iron to a magnet, or draws magnets to each other, works within a certain range of power, though a small one. Whereas if there is a magnetic power proceeding from the earth itself onto an iron needle and affecting its polarity, the effect would be working at a great distance. Again, if there is any magnetic force operating by agreement between the globe of the earth and heavy things, or between the globe of the moon and the waters of the sea, which seems very likely in the high and low tides twice a month, or between the starry heaven and the planets, all these things would be operating at very great distances. The last part of this quotation shows Bacon's awareness of and partial acceptance of the cosmic magnetic philosophy of William Gilbert, author of De Magnete, published in 1600, and the man who established that the earth itself is indeed a giant magnet. Gilbert used the earth's magnetic nature to provide a physical explanation for the three movements of the earth as required by Copernican theory. Bacon and others extended Gilbert's cosmic magnetism to explain other aspects of cosmology. Johannes Kepler, for example, used alternating magnetic attractions and repulsion to explain why planets move in elliptical, not circular orbits in his Astronomia Nova of 1609. This theory of cosmic magnetism, as proposed by Gilbert and endorsed by Bacon and Kepler, became highly influential in 17th century England. Furthermore, it even inspired a new version of atomistic philosophy. In 1674, Sir William Petit, who is best known as a pioneer of political arithmetic, published his new hypothesis of springing or elastic motions, in which he proposed that all things were constituted of atoms and that all atoms were spherical magnets. He was then able to explain, at least in a speculative way, the cohesion of atoms to form a stable body in terms of magnetic attraction, the expansion of bodies when heated in terms of increasing alignment of like poles with like poles, resulting in increasing repulsion between the particles, so giving rise to expansion, change of state from solid to liquid to vaporous, and numerous other physical phenomena, all dependent on the balance between attractive and repulsive magnetic forces. Now, Newton wrote in the preface to the Principia of 1687 that many things lead me to have a suspicion that all phenomena may depend upon certain forces by which the particles of bodies, by causes not yet known, either are impelled toward one another and cohere in regular figures, or are repelled from one another and recede. But William Petit had already been led to this same suspicion in 1674, but in his cases the causes were not unknown, but were, he claimed, magnetic attractions and repulsions. Now, Petit didn't explicitly state that his magnetic atoms acted on one another at a distance, but he didn't really need to, as we've already seen Bacon pointing out, quoting him again, whoever maintains the theory of the atom and the vacuum, even though he supposed the vacuum not to be collected by itself but intermingled through space, necessarily implies the action of the virtue of the atom at a distance. In between Petit's magnetic atoms there was only void. He did not imply, much less speak of, a continuous fluid ether capable of transmitting mechanical impulses from one atom to another. Similarly, he did not try to explain magnetic phenomena as Descartes had, in terms of streams of invisibly small non-magnetic particles travelling to adjacent magnets or pieces of iron and pushing or pulling them on them by contact action. So Descartes tried to explain magnetic attractions and repulsions away by imagining that magnets continually give off streams of particles, and indeed these would all be contiguous. There's no empty spaces in between these particles for Descartes. He's a planist, and these sort of streaming particles, you notice they're screw threaded, and so if there's pores going through magnets or iron, and so if a particle with a left-hand thread screw meets a pore with a right-hand thread, it will push it away. But if it meets a pore with a left-hand thread, then it will bore into it and draw the thing towards the magnet. So these things are not magnets, okay? But in Petit's system, these invisible things here are magnets themselves, and they are capable of operating at a distance. So the invisibly small particles for Petit are atom-sized magnets, and they operate on one another at a distance. And Petit could justify this non-mechanistic approach in good Baconian empiricist terms. All the motions I fancy in my atoms, he wrote, may be represented in gross tangible bodies. In other words, you can do experiments with actual magnets, and consequently may be made intelligible and examinable. So as far as Petit was concerned, experience showed, parce Descartes, that magnets were capable of acting at a distance. It was perfectly acceptable, therefore, to assume that his inaccessibly small atoms, which he couldn't directly experiment on or directly observe, but it was reasonable to assume, based on experiments performed with larger scale magnets, that they were also capable of acting at a distance. Okay, so much for the background. Let's turn now to see how things went with Newton. In 1679, Newton wrote a letter to Robert Boyle in which he tried to explain various physical and chemical phenomena by supposing that there is diffused through all places an ethereal substance capable of contraction and dilation, strongly elastic, and, in a word, much like air in all respects, but far more subtle. Now, Newton is rightly apologetic about the indigested nature, as he puts it, of these speculative explanations, and it seems that after dispatching the letter to Boyle, he began to consider more deeply the nature of strongly elastic fluids. The interim result of these musings was the unfinished De Aere et Aetheri, on air and ether. In this work, he did not simply take for granted that air and ether were capable of contraction and dilation, as he says here, but made it a major part of his concern to understand how these changes are possible. So starting from atomist or corpuscularian presuppositions, Newton assumes that rarefaction or dilation of air involves the constituent particles of the air moving further apart from one another. Condensation or contraction, by contrast, involves the particles moving closer together, crowding in upon one another. Furthermore, he knows from reports of experiments with the air pump conducted by Boyle and Hooke that air shows an amazing propensity to vigorously spread itself out to extremely rarefied states. The small amount of air in a deflated sealed bladder suspended in the chamber of the air pump, so just sort of hanging limply in the chamber of the air pump, will immediately expand itself spontaneously as soon as the pump is operated and the chamber, sort of a vacuum is created in the chamber. Indeed, the air will even burst the bladder in an attempt to spread itself throughout the chamber. Now, the glib explanation for this behaviour is that air particles are like tiny coiled springs, uncoiling themselves to their maximum extent in the bladder inside the air pump. But Newton dismisses this account very quickly. In fact, we've already seen him doing that in the quote I gave earlier. The levels of rarefaction are so great that the only safe assumption is that there are repulsive forces operating between the air particles. Furthermore, the rarefaction is such that the repulsion must continue to operate between the particles after they are already separated from one another. So we're not dealing with a single push off from one another when they're in contact, but a sustained repulsive force capable of holding the particles apart from one another for indefinite periods of time, and therefore operating at a distance. So given that the starting assumption is that there are only atoms and the void, this is another example of Bacon's insistence that whoever maintains the theory of the atom and the vacuum necessarily implies the action of the virtue of the atom at a distance. 1679 proved to be something of another annus mirabilis for Newton, because it was later in the same year that Robert Hooke wrote to Newton to ask his opinion of Hooke's own, to ask Newton's opinion of Hooke's cherished theory that Kepler's laws of planetary motion would follow if we were to assume the inertial motion of the planet and an attractive force operating between the planet and the sun, which varied inversely as the square of the distance between them. It was in this way that Newton came into possession of the universal principle of gravitation. The only thing Hooke couldn't supply was the mathematical proof that this was so, which of course was Newton's great achievement. Hooke was too cautious to write explicitly of actions at a distance, but his theory of planetary motions, inspired as it was by the theory of cosmic magnetism by Gilbert, Bacon and Kepler, and by the new hypothesis of magnetic atoms of William Petit, was certainly implicitly based on the Baconian assumption as expressed in the Novum Organum that we see repeated again here. If there is any magnetic force operating by agreement between the globe of the Earth and heavy things, or between the globe of the Moon and the waters of the sea, or between the starry heaven and the planets, all these things would be operating at very great distances. So in 1679, Newton concluded that there must be repulsive forces operating at a distance between particles of at least some kinds of body, like air and possibly ether, and was also persuaded by Hooke that there were attractive forces operating at a distance between particles of all bodies. Although he had unprecedented success in establishing the truth of the attractive forces in the Principia, he was less successful in understanding the repulsive forces. Even so, he was able to offer numerous suggestions as to how they might work and how the combination of attractive and repulsive forces might somehow explain all phenomena in the 31 queries that he added to the end of his optics. Given the astonishing success of the Principia Mathematica, it is hardly surprising that the queries came to be seen by the following generation of Newtonians as the most likely starting point for bringing Newton's enterprise to a successful, all-encompassing, fully comprehensive conclusion. Okay, now I move into another section, which subheading Enlightenment Newtonianism. I mentioned above that Locke's essay provided a ringing endorsement of the view that bodies cannot act where they are not. Given Locke's claim in his epistle to the reader at the beginning of the essay that the essay was intended to tidy up the rubbish that lay at the feet of a towering thinker like Newton, this endorsement of the pre-Newtonian view proves somewhat embarrassing. Locke's error was pointed out to him by Edward Stillingfleet, the Bishop of Worcester. They were engaged in a polemic at the time. Responding in 1698 to Stillingfleet's charge, Locke announced his intention to revise the next edition of the essay. I am since convinced by the judicious Mr. Newton's incomparable book that it is too bold a presumption to limit God's power in this point by my narrow conceptions. The gravitation of matter towards matter by ways inconceivable to me is not only a demonstration that God can, if he pleases, put into bodies powers and ways of operation above what can be derived from our idea of body or can be explained by what we know of matter, but also an unquestionable and everywhere visible instance that he has done so. And therefore, in the next edition of my book, I shall take care to have that passage rectified. In the 1700 edition, which was the next edition, Locke did indeed remove the anti-Newtonian passage, although he still couldn't bring himself to add an explicit endorsement of action at a distance. There were, however, many who did. I'm not sure how easy it is to see that. I mean, we needn't go through it, but that's just a list. Herman Boerhaave, Stephen Howes, John Rennie, James Hutton, favourite son of Edinburgh here. All of these are sort of using attractive and repulsive forces to explain all phenomena. We also spend a little time on Roger Joseph Boscovich, because he's going to figure later. He's the only Croatian Jesuit to figure in the history of science that I know of. Boscovich is credited with taking an aspect of Newton's speculations to its logical conclusion. Newton's speculations in the queries led some thinkers to recognise that matter was being replaced in the Newtonian system by the forces operating between particles. Samuel Clarke, in his famous published correspondence with Leibniz, insisted that Newton's philosophy proved, I quote, matter or body to be the smallest and most inconsiderate, he means inconsiderable, part of the universe. That's in 1715. Henry Pemberton, author of one of the first popularizations of Newton's system, published in 1728, wrote that the whole globe of the earth, nay, all the known bodies in the universe together, may be compounded of no greater a proportion of solid matter than might be reduced into a globe of 1 inch only in diameter, or even less. Similarly, Voltaire, in his Letters on the English of 1733, wrote of Newton that, examining the vast porosity of bodies, every particle having its pores, and every particle of those particles having its own, Newton shows, we're not certain that there is a cubic inch of solid matter in the universe, so far are we from conceiving what matter is. So Boscovich took up these ideas and postulated that there was no such thing as matter in the traditional sense. Bodies were made up of geometrical points, i.e. dimensionless points, endowed with inertia and with a force which manifested itself either as attractive or repulsive at different distances from the point. So this is there's the title of his work, Theory of Natural Philosophy, taken back or reduced to the only law of forces existing in nature. And going off here sort of asymptotically, this is the attraction of gravity, you know, sort of, this is a measure of the distance between the particles in question. And here we've got a sort of attractive forces increasing this way and repulsive forces increasing this way. So as you get as the bodies get further apart, the distance increases. Then the attractive force diminishes asymptotically towards the 0 point, but of course it never reaches 0. So there's a sense in which the attractive force carries on to infinity, but as you come closer it increases, and then here sort of, this is now speculation on Boscovich's part, but he's trying to do the same kind of thing that Petit was doing with his magnets. He wants to explain things like elasticity and you know, change of state from solid to liquid and so on in terms of a balance of attractive and repulsive forces. So we get this sort of area as you approach a body where you get switching from attractive to repulsive forces, but as you get very, very close, attractive force increases in accordance with the inverse square law, but then when you get to a certain closest, immediately this shoots up to very, very strong resistive force. So the particles that make up this desk here have a very, very strong repulsive force, and I can't push my fingers through them. Okay, so that's Boscovich's refinement, if you like, of Newtonian physics. Okay, so needless to say, what we are dealing with here are forces operating at a distance between the geometrical points. There's no suggestion that the points are embedded in a continuous substance capable of providing a mechanical account of the behaviour of these points. Boscovich's ideas proved amazingly influential. They were taken up in England by the Newtonian chemists Joseph Priestley and Humphrey Davy, and by the brilliant experimental philosopher Michael Faraday, and subsequently his ideas were amalgamated, I believe this is true, though I'm not an expert in this area, his ideas were amalgamated with the similar ideas of Immanuel Kant to give rise to a Newtonian tradition within German Naturphilosophy. Okay, end of section, new section, Immanuel Kant, Newtonian. Now we needn't go into the details of Kant's dynamic theory of matter here. I'd be too nervous to do so in front of McKenna. My concern here is simply to show you that Kant's theory was Newtonian and depended therefore on actions at a distance. Kant's earliest contributions to natural philosophy, what we would think of as scientific writings, both showed Newtonian influence. The Universal Natural History and Theory of the Heavens of 1755 presented an earlier version of what later became known as the nebula hypothesis, and showed how the Milky Way and our solar system could have emerged from a cloud of hot gaseous material if we assume the truth of Newton's universal principle of gravitation. The physical monadology of 1756 sounds from its title more Leibnizian than Newtonian, but Kant uses Newtonian notions to solve a problem confronting Leibniz's theory that the ultimate constituents of all things are indivisible monads. The problem was that monads were held to occupy a given volume of space, which seemed to deny their indivisibility. A dimensionless point can be accepted as indivisible, but an entity with dimensions must be, at least in principle, divisible. Kant's solution to this conundrum was ingenious and also thoroughly Newtonian. The actual substance of a monad, he suggested, was confined to a geometrical dimensionless point, but the point was the centre from which emanated attractive and repulsive forces. The seeming three-dimensionality of the monad stemmed from repulsive forces in a sphere of activity emanating from the geometrical point and giving it the appearance of a sphere. So this sphere can be said to be divisible, but the monad at the centre of this sphere, a dimensionless point, remains indivisible. Now I hope you can see straight away that Kant's physical monadology shows a striking resemblance to Boscovich's theory of geometrical points endowed with attractive and repulsive forces, though as far as we can tell these theories were developed independently of one another. Kant's fullest discussion of his dynamical theory of matter appears in the Metaphysical Foundations of Natural Science of 1786. Here the assumption is that all physical phenomena, hardness and softness, condensation and rarefaction, elasticity and so forth, can be reduced to the interplay of forces of attraction and repulsion between the constituent particles or material points of bodies, so entirely Newtonian. Leibnizian monads seem to have dropped out of the picture by now, to be replaced simply by geometrical points acting as sources of attractive and repulsive forces. So this might have been under the influence of Boscovich by now, but I don't know. I'm not an expert on Kant. I'd like to look at that, or maybe be told about it. Anyway, now Kant had his own philosophical agenda, and we needn't pursue that here. But let me just provide a couple of quotations to show that Kant's, I say a couple, I think it's 4, to show that Kant's Newtonian natural philosophy was based on the premise that motive forces were perfectly capable of acting at a distance. These are all from chapter 2 of the Metaphysical Foundations. So the action of one matter on another in the absence of contact is action as a distance. This action as a distance, which is possible even without the mediation of matter lying in between, is called immediate action as a distance, or the action of matters on one another through empty space. And again, the action of a moving force that is independent of all contact is also independent of the filling of space between the moving and the moved. That is, it must also take place without the space between the two being filled, and thus as action through empty space. Hence, the original attraction essential to all matter is an immediate action of matter on other matter through empty space. Again, same chapter. The most common objection to immediate action as a distance is that a matter cannot act immediately where it is not, as we saw right at the beginning. When the Earth immediately impels the Moon to approach it, the Earth acts on a thing that is many thousands of miles away from it, and yet immediately. The space between it and the Moon may well be viewed as completely empty, for even though matter may lie between the two bodies, it still contributes nothing to this attraction. It therefore acts immediately at a place where it is not, which is apparently contradictory. In truth, however, it is so far from being contradictory that one may rather say that everything in space acts on another only at a place where the acting thing is not. Haha. So take that. And this is my favourite. And this links up to things that Thomas was talking about earlier. Well, let me read the quote first. It is commonly supposed that Newton did not at all find it necessary for his system to assume an immediate attraction of matter, but with the most rigorous abstinence of pure mathematics, allowed the physicists full freedom to explain the possibility of attraction as they might see fit, without mixing his proposition with their play of hypotheses. Okay, so this is the sort of background, if you like, he's referring to where Newton says hypotheses non fingo, you know, I'm not sort of giving an explanation for gravity, you know, I'm just sort of talking about it mathematically, and, you know, it may be explained any way you like, you know, that's, and Kant is referring to this. But see how Kant goes on. But how could he ground the proposition that the universal attraction of bodies, which they exert at equal distances around them, is proportional to the quantity of their matter, if he did not assume that all matter, merely as matter, therefore, and through its essential property, exerts this moving force? So I was so pleased when I read this, because I've always thought this is exactly how I've been thinking when I've read Newton. He must have believed that there was an attraction as a distance, and here's Kant making exactly the same conclusion. Thus, one cannot adduce this great founder of the theory of attraction as one's predecessor if one takes the liberty of substituting an apparent attraction for the true attraction he did assert, and if one assumes the necessity of an impulsion through impact to explain the phenomena of approach. So if you do that, you're not a true Newtonian. You know, the true Newtonian is the chap who does accept, you know, that things are capable of acting on one another at a distance. Okay, so I rest my case with regard to Immanuel Kant. So the reassertion of the principle, the subheading for this next section is the reassertion of the principle that a thing cannot act where it is not. Okay, so Kant's only one example, albeit a very important one, showing that Newton's authority was so powerful that, for a while at least, it overcame the age-old prejudice that a thing cannot act where it is not. But it wasn't to last. The history of 19th century physics is a history of the decline of Newtonianism and a replacement of dynamics with the kind of kinematics advocated centuries earlier by Galileo and Descartes, where only bodies in motion could be invoked in physical explanations, and talk of forces of attraction and repulsion acting across empty space were rejected as completely untenable. Now, there are, of course, many factors involved in this historical process. One important factor, for example, was the development of the kinetic theory of gases, the spontaneous inflation of a bladder in the chamber of the air pump that we were talking about earlier, was now no longer seen as a result of repulsive forces continually operating between the particles of air, but as a result of the incessant motions of the particles continually hitting the skin of the bladder, bouncing off, hitting the other side of the bladder and so on. So countless impacts of countless particles kept the bladder inflated. So it's motion of the particles, not forces, that are keeping the bladder inflated. Similarly, the wave theory of light required a continuous ether through which light waves were propagated, and this gave rise to continuous theories of electricity, magnetism, and even gravity. Meanwhile, theories about the curvature of space were also being developed to explain gravity away by seeing it as nothing more than the result of planetary motions following contours in space created by the sun or other space-deforming bodies. Again, we can't follow all of these developments here, but I want to indicate by way of bringing this survey to a conclusion that one of the factors involved in the decline of the Newtonian belief in action at a distance was the authority of Newton himself. Let's start with an interesting quotation from the leading 19th century experimental physicist Michael Faraday. This is in a brief essay published in 1844, Speculation Touching Electrical Conduction and the Nature of Matter. And he wrote, "The view now stated of the constitution of matter would seem to involve necessarily the conclusion that matter fills all space, or at least all space to which gravitation extends, including the sun and its system. For gravitation is a property of matter dependent upon a certain force, and it is this force which constitutes the matter. In that view, matter is not merely mutually penetrable, but each atom extends, so to say, throughout the whole of the solar system, yet always retaining its own centre of force. Hence, matter will be continuous throughout." Now, I'm not sure how clear it is to you from this quotation, but the view now stated of the constitution of matter in this essay is in fact a Boscovichian view, similar to the Kant's view in the physical monadology that we've already looked at. Okay, so this is what he means when he says, the force goes on to infinity, goes out throughout space. He's referring to this, infinite extension of this sort of asymptotic line in the Boscovichian diagram. Matter consists of dimensionless points which are endowed with attractive and repulsive forces. It could easily have been the case, therefore, if we indulge in a bit of counterfactual history for a moment, that Faraday might have continued the Newtonian tradition of dynamic matter continually operating at a distance. In fact, if we go back to that quote, he is saying things like, that matter is mutually penetrable. So he doesn't seem to have an idea of matter as, solid body, and each atom extends throughout the whole of the solar system, because, and he says, dependent on it is this force which constitutes the matter. So it's very much like this sort of Boscovichian view, and Faraday therefore could have, as I say, perpetuated the idea of action at a distance into the 19th century, but of course he didn't do that. So if we return back from counterfactual history to real history, Faraday developed this idea into his theory of force fields, in which he insisted the lines of force were real physical connections between bodies. Not quite sure what he means by physical though. He saw this as being a rejection of action as a distance. And Faraday has been described by F.H. van Lunteren, quite rightly I think, as, I quote, the first notable physicist to publicly oppose the notion of action as a distance in its generality. Now, one of the reasons he felt it was so important to reject actions at a distance was his belief that Newton had vigorously condemned them. Writing in 1855, for example, he cited a particular crucial passage from Newton which seemed to vigorously deny action as a distance, and insisted upon the strong conviction expressed by Sir Isaac Newton that even gravity cannot be carried on to produce a distant effect except by some interposed agent fulfilling the conditions of a physical line of force. Okay, now Newton's supposed condemnation of actions at a distance that Faraday is referring to here occurs in a private letter which he wrote to the Anglican divine Brigitte Bentley in 1693. This letter was first published in 1756, when Newton's brief correspondence with Bentley was published as 4 letters from Sir Isaac Newton to Dr. Bentley containing some arguments in proof of a deity. Now at this time, 1756, the action at a distance physics of Newtonianism was at its height, and nobody, as far as I know, noticed this statement, which we're going to look at in a minute, as a contradiction of action at a distance by the great man himself. By the time these letters appeared in print again, however, things had changed. In 1838, when physics was already turning away from actions at a distance, the letters were republished in a work, Richard Bentley, Sermons Preached at Boyle's Lectures, Remarks upon a Discourse of Free Thinking, Proposals for an Edition of the Greek Testament, etc., etc., and the 4 letters are in those etceteras. Okay, so this is in 1838. Now this statement by Newton in one of the letters to Bentley is seized upon by physicists wanting to use his authority, like as Faraday did, to justify their rejection of actions as a distance. And indeed, quoting F.H. van Lunteren again, he suggested that, I quote, the phrase in the 3rd letter to Bentley must have been Newton's most frequently quoted statement in the second half of the 19th century. Okay, before I show you this statement by Newton, let me explain the background. Bentley was about to publish a work of natural theology in which he used Newton's natural philosophy to combat atheism. Anxious not to damage his case by misrepresenting Newton, he wrote to Newton to check he had things right. And at one point he wrote, so these are Bentley's words, "'Tis inconceivable that inanimate brute matter should, without a divine impression, operate upon and affect other matter without mutual contact." Now, I hope you can see that Bentley is not saying action at a distance is absolutely impossible or inconceivable here. He's saying it is impossible for matter to act at a distance unless God makes it possible. Right? So this is confirmed also by the way this idea was expressed in the published work. So the first quote here is in the letter to Newton. You'll see Newton's reply in a second, and then this is what appears in print after his exchange with Newton. That such a mutual gravitation or spontaneous attraction can neither be inherent and essential to matter nor ever supervene to it unless impressed and infused into it by a divine power. Okay, so in the reply to Bentley's letter, to the first quotation, Newton writes, "The last clause of the second position I like very well." Okay, so that's the that's the last clause of the second position. Okay, I like very well. "It is inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate on and affect other matter without mutual contact." Okay, so I hope you can see that Newton is simply repeating the same point here as Bentley made. Right? He's not saying that action at a distance is impossible. He's simply endorsing what Bentley said. He's not disagreeing with Bentley, he's endorsing what he said, that this is impossible, action at a distance is impossible unless we have the mediation of something else which is not material. Now this is not as clear as Bentley's talk of a divine impression, but it's clearly a reference to God. We're not talking about a material medium here required to transmit action from one body to another. Newton is talking of mediation or intervention by God to endow matter with the power of acting at a distance. So he's agreeing with Bentley. Unfortunately, however, Newton over-egged the pudding and went on to labour his point, and in so doing he garbled the issue. Remember, this wasn't meant for publication, he's just writing a private letter. He garbles the issue and makes it very easy for 19th century readers and indeed 21st century philosophers and scholars to read him as though he was simply rejecting out of hand any notion of action at a distance. So this is how the entire passage reads. The last clause is the second position I like very well. It's inconceivable that inanimate brute matter should, without the mediation of something else, which is not material, operate upon an effect of the matter without mutual contact. As it must be if gravitation in the sense of Epicurus be essential and inherent in it. And this is one reason why I decide you would not ascribe innate gravity to me. That gravity should be innate, inherent and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Right? So this does look, I admit, as though Newton is simply, rejecting action at a distance out of hand. This is the really damaging part of the quote, by and through which their action and force may be conveyed from one to another. That sounds as though he is talking about mechanical transmission between bodies there. But I would say, I saw people nodding their heads when I was sort of explaining how we should read this first part of this quote. He's agreeing with Bentley there, and here he's just sort of carried away by the exuberance of his own verbosity and trips himself up. But as I say, he obviously didn't notice that he'd done it. Neither did readers in the 18th century, and after it was first published in 1756. Certainly I've never come across anyone. And Bentley himself, sort of uses the same idea in the actual published version of the lecture. Okay, so irrespective of what Faraday and other 19th century physicists wanted to find in this quotation, Newton is trying to make the point, agreeing with Bentley, that gravitational attraction is an action at a distance, and its manifest existence, therefore, because we all know that gravity exists, its existence proves the existence of God, because it is unconceivable, as Bentley said, it is unconceivable that inanimate brute matter should operate upon an effect of the matter without mutual contact, without a divine impression. We've already seen the theological point underlying Newton's and Bentley's view expressed by John Locke when he wrote to Edward Stillingfleet. The gravitation of matter towards matter by ways inconceivable to me is not only a demonstration that God can, if he pleases, put into bodies powers and ways of operation above what can be derived from our idea of body, but also an unquestionable and everywhere visible instance that he has done so. So that's what Bentley and Newton were trying to, establish in, after all, they're talking about how Bentley can best use Newton's ideas to prove the existence of God. That was what the whole correspondence was about. This is the John Locke himself, a few years after the correspondence. The correspondence is 1693 here. Now Locke has obviously spoken to Newton and got the same idea from him. So the mature Newton never did reject the possibility of actions at a distance, not even in his letters of Bentley. On the contrary, his endorsement of them, of actions at a distance, in the optics and elsewhere, led to their being taken up and deployed by leading Enlightenment thinkers. This in itself is remarkable testament to the authority of Newton. Who else but the author of the Principia could have persuaded thinkers to reject the deeply entrenched prejudice that a body cannot act where it is not? And indeed, so great was his authority that when physicists decided that the way to move forward was by abandoning dynamics and returning to a mechanistic kinematics, they still felt the need to invoke Newton's authority against actions at a distance. That single passage from the letter to Bentley and their ignorance of the history of Newtonianism enabled them to do so. The fact remains, however, that Newton himself believed in the possibility of actions at a distance, and his 18th century followers took it for granted. Okay, that's the end.